So welcome everyone. I think people will keep joining over the next minute or two as we get started, but we've got a full hour of presentations and questions coming up, so I think we should go ahead and get started. So my name is Dan Lipson. I'm a research soil scientist at the Soil Health Institute. I'm one of the co-organizers of this seminar series. And before we get into the talks, there's just a few things that I want to go over. The first is that if you need help or you have any questions for the speakers, you can use the questions tab on the control panel, and you'll get your response back individually if you're having help. We're going to use as a way to kind of engage people outside of the seminar. We're going to use something called a Padlet, and so you'll see the link to that on your control panel as well, and you can go ahead and introduce yourself there, ask questions, and follow up on what we're talking about today. And then I just wanted to have a quick reminder that our next seminar will be August 17th on when does increased carbon storage yield net removal of greenhouse gases. And so with that, I think we should go ahead and get started with our first speaker. Our first speaker is Dr. Jonathan Sanderman, who's an associate scientist with the Woodwell Climate Research Center, and he studies the role that soils can play in climate mitigation and sustainable food production. Prior to joining the Woodwell Center, Dr. Sanderman was a senior research scientist and team leader with Australia's National Science Agency, CSIRO, and John strives to understand the processes that add, remove, and transform carbon in soils, ranging from coastal marshes to tropical forests and working farmlands. His research encompasses both place-based experimental work and large-scale computer modeling. And so with that, take it away, John.
Okay, Dan, thanks so much for the introduction. And I really, really appreciate this opportunity to talk to this webinar and really just be part of this great series of talks that this group has lined up. And I just want to begin by acknowledging my collaborators at Environmental Defense Fund, and particularly Emily Oldfield, who's really helped shape my thinking on this topic over the past year as we continue to explore the world of soil carbon markets. Now, I've been showing some version of this slide at talks over the past few years, and the point that I usually make is that soil science has kind of been stuck with these old-fashioned, almost Neolithic tools and 50-year-old analytical methods, but there's really a lot of really neat innovation going on in this space, really bringing soil science into the big data era, taking advantage of all these data streams that have been available to agronomists and forest-related disciplines for a long time. So today, what I want to do is kind of three parts. First, I'm going to start by highlighting that there's often a large disconnect between how academics see this issue and how emerging carbon markets view soil carbon monitoring. Then I want to talk about why it's so difficult to detect change and why a lot of technology and innovation is really needed. And finally, I'm going to run through a short list of emerging technologies and just kind of touch on some of the advantages and disadvantages of some of these emerging approaches. So I just want to start by saying we know how to measure soil organic carbon stocks. It's just expensive to do well. So it's really all about the cost. Now, Australia has a really good measurement-based protocol, but CSIRO has estimated that it currently costs about $30 per hectare to monitor soil carbon change under that protocol. And as a result, uptake of farmers entering into the program has been pretty slow. And so recently, the Australian Minister of Energy and Emission Reductions announced well over $100 million in funding to really try to drop this cost by 90%. So they set this goal of carbon monitoring at $3 per hectare, thinking that they want to be able to pass on most of the profit of the carbon credits to the farmers and not eat it up through monitoring and verification. Now, this is a typical sample design in an academic study. It's really nice data-driven sampling design, taking advantage of already available information on the farm, taking triplicate cores down to 90 centimeters at 100 locations, dividing each of those cores into 10-centimeter increments for analysis. Now, this is great for an academic study, but it literally costs tens of thousands of dollars. And kind of alternatively, most of our knowledge on soil carbon change really comes from replicated controlled field trials where the spatial variability is really constrained, and so we maximize our chance of detecting change with a small number of samples. Now, to contrast, what we usually do as academics with what carbon markets are really developing, carbon market protocols are really ranging from measurement only to model only or practice-based approaches. So just paying farmers for adopting certain practice, and we believe certain practices result in a certain level of carbon sequestration. And so on the measure only protocols, they really only require a handful of samples for a farm, but they do require a certain level of statistical certainty that the change was real. And so that actually drives up the actual number of soil samples that you need to collect. Now, most of the protocols, as you can see, kind of fall into this hybrid space using a combination of measuring and modeling. And this is really recognizing the fact that we know we can't measure and detect real change year over year, but we can use models to credit these in-between years where if we go in and we need at least 5 years or so probably to detect change in the measurement only protocol. But if we use models, then we can start crediting farmers year after year and use the measurements to true up how the models are performing. Now, there's a large number of third-party voluntary markets that have really come on board in the last 12 months, and they're really mostly focused on model-only protocols. And that's really primarily driven because they want to minimize transaction costs and really try to transfer most of the value of the carbon credits to the farmers. But obviously, it's much harder to verify that real change is occurring if you're only using models and not making any measurements. And also I'll point out that there is one protocol by the Regen Network that is really based on a remote sensing approach that's out there. Now, moving on, can we actually detect change in soil carbon? And really the first thing I want to ask is how much change are we expecting to see? Now, most models predict similar outcomes as what I'm going to show here. So these are just a couple of meta-analyses, one that I did about 10 years ago, looking at Australian cropping best management practices. So we get a mean value of 0.3 tons of carbon per hectare per year with a lot of spread around that mean value. A really nice meta-analysis of cover crops also showed a mean value of about 0.3 tons of carbon per hectare per year. And just a few years ago, Rich Conant updated his meta-analysis of grazing management impacts on soil carbon and also found a mean value of about 0.3 tons of carbon per hectare per year. So 0.3 tons of carbon change against a large background is really hard to find. It's really like detecting a needle in a haystack. And so I just want to walk through a quick example. So this is about a 1,000-acre property in Colorado that I've been working on. It's a mix between irrigated alluvial soils and dryland sloping soils. And so you can actually see in this map the real big contrast between soil carbon levels in the irrigated fields and the dryland portions. And this is, we get a really typical distribution of soil carbon. So this is actually, what I'm showing here is actually just a 100-meter resolution soil carbon map by Ramcharan and et al. That was published a couple years ago for the contiguous United States. And so these spatial maps, they're not a perfect or true representation of reality, but they're really useful to look at sample variance and ability to detect differences. And this is the histogram of the distribution of carbon at this site. Get a mean of 22.8 grams of carbon per kilogram with a standard deviation of about 5. And this is really typical that your standard deviation is 20–25% of the mean soil carbon value. We see that at a lot of scales across a lot of farms throughout the world. Now we can do some simple back of the envelope math. If we assume the average soil carbon value is about 2%, just assume a bulk density of 1 gram per cubic centimeter, carbon stocks are 60 tons. And so if we're looking for a change of 0.3 tons of carbon per hectare per year, we're looking at an increase from 60 to 60.3 tons of carbon per hectare annually. Now, if there's no change in bulk density, we're only talking about a 0.01% increase in carbon concentration. This is really, really, really hard to detect. And even after 5 years, we're really only talking about 0.05% increase in soil carbon concentration. Now, several protocols recommend conducting a power analysis, which you can do based on prior information, such as that soil carbon map I just presented to help inform your sample design. And so this is some typical results from a power analysis. And that field I showed really tracks along the blue line for standard deviation of about 0.5% soil organic carbon. Now, to detect a change of 0.3 tons of carbon per hectare per year after 5 years, we would actually need to collect 30 samples per hectare. And even at the low end of field variance, about 0.3% organic carbon, we're still talking about 8 samples per hectare to detect change with a power of 0.8. Now, a critical way to decrease the cost and decrease uncertainty is to aggregate many farms into one project. Now, variance in soil carbon has to be bounded. And we see that whenever we look at spatial variance in soil carbon. So this plot on the left is a variogram of soil carbon variance between different points throughout the United States and Mexico, but we see very similar semi-variograms, pretty much whatever scale we look at for soil carbon. It's really showing that the spatial variance levels off at plateaus after a certain spatial scale. And because of that, if we increase our size of our project, instead of just looking at one farm, looking at a number of farms over increasing areas, we actually see that the sampling density required to detect the same level of change in that last example drops as a power function. So this is an analysis that my colleagues at Granular put together using a similar soil organic carbon map as I presented earlier. And what's amazing about this analysis is the actual number of samples you need to collect stays about the same regardless of the scale you're looking at, because we're increasing our power to detect change, because our variance doesn't keep increasing as the project size increases if we start aggregating lots of farms together. And so obviously our ability to detect change goes way up, but one of the downsides of aggregating a bunch of projects is all the enrolled farms will then receive the same mean credit. And so a lot of the carbon markets really want to credit the individual farmer based on the management that they're applying. And so you would have to accept that everyone gets the same mean outcome in an aggregated project structure. Now, increasing project scale also greatly reduces model uncertainty. So Bill Salas at Regrow shared this slide with me. And basically what we're looking at is a Bayesian implementation of the DNDC soil carbon model at an increasing number of fields in the project. Now, most of the major process-based models are really deterministic. So for a certain set of input conditions, you get an exact outcome. But in this Bayesian approach, we're really trying to propagate uncertainty in all the input variables and all the model parameters to really look at the actual range of possible outcomes from that model. And you can see in the upper left, if we just run the model from one farm, we have large variability over or centered around a small positive carbon sequestration value. But as the number of fields in the project increases, the standard error about that mean sequestration rate goes way down. And this table in the bottom right really shows that our error decreases from about 200% down to 10% as we move from 1 to 1,000 farms in this aggregated scale. Now, a related issue that I want to discuss here is the idea of a baseline. In a measurement-only protocol, we have to assume a static baseline, and any change in soil carbon is strictly due to additions of soil carbon in the project. But the reality is our business as usual case is going to vary for a number of reasons throughout the duration of our project. That includes the historic management before the project was implemented, but also the climate over the crediting period. If we have wetter than usual years or drier than usual years, our soil carbon values are going to change. As a result of this, most of the protocols are actually requiring or recommending a dynamic baseline, such as drawn on the right in this diagram. Now, it is important to note from the atmosphere standpoint, both of these cases result in the same net benefit, but our measurements really need to be different to validate both of these approaches. And I think just to drive home this point, I wanted to bring up some data that I collected in Australia from a bunch of long-term field trials adopting best management practices. In fact, we really showed that, these trials really showed that it's mitigation of ongoing losses that's driving all of the net benefit in these cropping systems. So the business as usual farm treatments are all losing carbon at a rate of about 0.3 tons of carbon per hectare per year. And the best management practices are basically just mitigating those losses. And so in this case, if we're not tracking that counterfactual, we actually would be ascribing zero net benefit to these improved management practices. Now, model-based protocols, as I said, generally track the counterfactual or business as usual scenarios. This is just a screen grab from SIBO Technologies Carbon Platform, which is based on Bruno Basso's SALIS model. So in this theoretical example, you can see that the regenerative field is sequestering a lot of carbon, 6.4 tons of CO2 equivalent captured by the soil. But if you look in that purple box under the conventional line, we see that actually the conventional farm is sequestering almost the same amount of carbon, and so the net soil carbon benefit is almost zero on this field. The other point I just wanted to quickly make on this slide was that all of the net greenhouse gas benefit in this project is really from reductions in N2O emissions, decreases in diesel fuel use, and decreases in emissions related to their fertilizer production. And so it's really important to track all greenhouse gases, not just soil carbon in a project. And I know this is going to be the topic of the next webinar in this series. Now, to move on to a short list of technologies, I want to touch on how we can optimize sample design to reduce the number of samples we need to collect, how lab-based technology such as spectroscopy can minimize our analytical costs, and then talk about emerging in situ sensing technologies to eliminate the lab altogether, talk a little bit about remote sensing technologies, and touch a little bit more on models and modeling. Now, optimizing sample design really isn't a new technology, but I wanted to bring it up here because there's a lot of current research and interest in building optimal sample designs for supporting soil carbon projects. And so this is that same farm I showed earlier. You can see we could stratify based upon prior information with this data-driven sample selection. And so here we clustered the field into 5 clusters and then sampled proportional to the clusters, and drawing only 50 samples from this 1,000-acre mixed-use property, we can actually get within 0.03% of the mean value. So these data-driven sample design approaches are really important for driving down the number of samples we need to collect to get a good representation of the mean. Now, there's been a lot of work looking at field scale optimization. I would argue there's been very little research done thinking about how to design a sampling strategy at scale for these aggregated projects that I was talking about earlier. Now, this figure is just an idea myself and colleagues at Environmental Defense Fund have proposed around the stratified sampling and reporting protocol. And the different colors in this figure are representing the technology extrapolation domains, which are basically similar biophysical soil regions where the same production system should result in similar yield results, and lessons learned from one production system within the same TED domain should be transferable to that same TED domain in other regions of the country or even other regions of the world. So basically what we've done here is we've proposed a nested design where we essentially stratify within USDA agricultural statistic districts using these TED fields as a way of aggregating our samples. Now, next up, this is really one of my favorite technologies to minimize costs in the lab. So soil spectroscopy, which includes different forms of infrared spectroscopy and laser-induced breakdown spectroscopy, have all really been shown to do a really good job estimating a range of chemical and physical soil properties. And the basis for this method is simply as follows. On a training set of samples, we collect in this example, mid-infrared spectra. We combine it with analytical data. We build multivariate or machine learning models, which you could then apply to samples that we only collect the spectra on and get predictions. We could predict with uncertainty. And this system with good training sets and good models does really well for properties like organic carbon, for texture, carbonate, cation exchange capacity. It's probably about 15 or 20 soil properties where this lab-based technology can do a pretty good job estimating the soil properties. And this is just one example from a recent publication coming out of my group using the Kellogg Soil Survey Library built by the US Soil Survey Lab in Lincoln, Nebraska. We could do an excellent job predicting the number of soil properties simultaneously. And this is just an example of one soil vertisol from Kerr County in Texas, looking at organic carbon, carbonates, cation exchange capacity, clay content, and pH. You can see the spectroscopy-based estimates in the dots and the reference analytical data in the gray lines. So we're doing a really good job, and I think this system has been shown to work really well. And it's really good when you want to look at a lot of soil properties, but it's still really time intensive. So we're reducing the final analytical costs, but we're not eliminating the need to collect the soil sample, process it, and grind it before analysis. And so over the past decade, there's been a lot of research and development, let's say over the past several decades, really, into field-based soil sensors. So I'm going to leave most of this discussion on this topic to Cristine's talk. But obviously, eliminating the need to collect soil samples and send them to the lab is going to be a huge cost savings. Now, in the center on the right, these tractor-pulled or autonomous robot-driven systems have similar drawbacks to a remote sensing-based approach in that they're only measuring the soil surface, or in the case of this tractor-mounted one, dragging the sensor just a few centimeters below the soil surface. On the other hand, we have sensors such as this yardstick technology that are drilled or pushed into the ground, can give you more of a three-dimensional look into the soil. Now, one of the downsides of the field-based spectroscopy is that there's all the heterogeneity in the soil that we still have to deal with, which is going to introduce more uncertainty into our estimation. So variable levels of moisture, living roots, and soil macrostructure can all influence the quality of the predictions from these field-based sensors. However, as long as these estimates are mostly unbiased, our precision and accuracy, we can sacrifice some precision and accuracy because of the greatly increased number of samples we could collect for the same effort. So what about remote sensing? So there's a lot of research interest in the topic, and I think a lot of really good advances being made, especially with some of the new sensors that are being sent into orbit. However, in my opinion, there's some fundamental limitations. The first, as shown in this figure, is there's actually very little bare ground, and we're actually trying to get farmers to keep ground covered at all times. So the percent of bare ground is just going to keep decreasing over time. So the number of usable remote sensing scenes are going to keep decreasing as long as farmers keep listening to agronomic advisors. And I'd also say that research has generally been focused just on estimating carbon concentration, but we can't really forget that we need to get bulk density and gravel content to calculate carbon stocks. And these are properties I think are much harder to estimate from any sort of sensing solution. And the last main drawback of spectroscopy is that remote sensing based spectroscopy is that we really are only seeing the top few millimeters of soil. So any prediction of an entire soil profile is strictly by indirect correlation with whatever we're seeing at the surface. And we know the down profile relationships with soil carbon, bulk density, and other properties vary both by soil type and by management. And so it's going to be really hard to build high quality predictive models if we're only seeing the surface and not seeing the whole soil profile. And this slide here really shows why remote sensing for carbon is difficult. And so these are actually visible near infrared spectra for dry vegetation in yellow, green vegetation in green, and then In between them are soils with increasing carbon content from orange, red, brown, and purple. And so we can see that the dry versus green vegetation basically completely bounds our soil values. So if we have any vegetation, whether it's green vegetation or stubble, all the remote sensing is going to be seeing is that vegetation, and you're not going to be seeing that soil carbon signal, and it's going to make it really hard to make accurate soil carbon models. In fact, the authors of this paper actually found that if they had a very strict exclusion criteria, so they were really confident they were only measuring bare ground, their models were quite good. But as soon as they relaxed those criteria and included soils with variable moisture, any stubble, or any green vegetation at all, the models completely fell apart. So I included models also on this list of emerging technology because most protocols are promoting their use, and there's a huge amount of academic interest in this topic. And there's just a few points I wanted to make here. So the markets and protocols are currently dominated by just a handful of traditional models, yet there's a huge diversity of models out in the academic literature that do a much better job representing modern concepts of how we think carbon is stabilized or lost from soils. Yet there's been almost no discussion about incorporating these models into carbon protocols at this moment. There's a really high degree of user skill that's required to run these models, which makes it really hard for groups to feel confident that they're using these models accurately. And there's, as I mentioned earlier, these models are primarily completely deterministic. So there's a lot of debate over how we properly represent uncertainty in the model. One of the things that's interesting in the soil carbon space, unlike the climate space, is multi-model ensembles are still primarily lacking. I mean, climate scientists would never run one model to predict future climate outcomes, but for some reason, the soil carbon community feels comfortable just picking one model and sticking with it. And the last point I wanted to make is there's really an extremely limited supply of good data sets for model training and validation. And so not only does that limit the applicability of the model, so there are just a few management practices where we have good data, it also makes it really hard to assess the uncertainty if we have just a few dozen good training sets in this country. Now, I wanted to sum up my survey of this technology by talking about the Indigo Carbon Challenge. So during 2019-2020, Indigo Ag held an innovation competition for quantifying soil carbon, and dozens of companies developing all sorts of interesting tech solutions to carbon monitoring entered the competition. These included robot-based field sensors, drones, and remote sensing companies. And the winner was Laser Ag, which is a company that has been utilizing this well-developed lab-based spectroscopy method, laser-induced breakdown spectroscopy. And kind of my takeaway from the winner of this competition was, it says a lot about the readiness level of a lot of these field-based technologies, that something that still required all the effort to collect the sample in the field, bring it back to the lab, demonstrated that it was more accurate and more cost-effective than these field-based technologies at this point. Really says that we're probably several years away from really seeing wide-scale deployment of some of these more novel field-based sensing approaches. So with that, I'll just conclude and say we know how to measure soil carbon. It's just expensive because of the spatial variability. There's a lot of really neat technological developments that are needed to reduce costs and are currently happening. We know how to take advantage. So for example, we know how to take advantage of ancillary data to optimize sample design. Lab-based spectroscopy is a pretty mature technology. It can help, but it doesn't eliminate the cost of field work. Third, aggregation is absolutely critical and really needs a lot more focused research to understand what are the best sampling and model design strategies for working with these aggregated projects. And finally, given much of the greenhouse gas benefits from improved management really come from reduced emissions, measuring the counterfactual scenario is critical, but there's currently very little discussion as to how we should do it. And with that, I'll just thank everyone for listening, and I'm happy to take questions.
Okay, well, we're down to about 1 or 2 minutes for questions here.
Oh,
So
sorry, Dan.
no, it's okay. It happens. So while we're kind of switching over to the next speaker, so it came up in the questions people asked when they registered and in the questions here, but you mentioned, the importance of bulk density and doing these calculations too. Do you want to just talk for a minute about if we're making any progress on how to measure bulk density too?
Yeah, certainly. I mean, I think the first point I want to make is if you actually look at studies that look at where the variance in soil carbon stocks come from, invariably most of the variance comes from carbon concentration, not bulk density. So in fact, my colleagues in Australia did a study. I mean, granted, the soil diversity was low, but over 95% of the variance in soil carbon stocks came from carbon concentration. Only about 4% of the variance was from bulk density. So, and I've seen similar studies in the US where it's about 80-20 split. So a little more importance of bulk density. But I mean, I think the point there is it is really about measuring carbon concentration well. But to get at technologies for measuring bulk density, it is interesting. There's been a lot of work with kind of like neutron sensors and other technologies kind of coming from the more engineering, like road paving disciplines, and they seem to work pretty well. The Truxel is one brand that has been tried and seems to work pretty well, but they're expensive. So it's hard to say. So yeah, I don't have a good answer to bulk density.
No, but I think that's helpful. I think that's helpful for people.
If we do a really good job of carbon concentration, we don't have to worry as much about bulk density.
Great. Well, thank you, John. And so now we're going to switch over to our second speaker, who's Dr. Cristine Morgan, and she is the Chief Scientific Officer for the Soil Health Institute, where she works with diverse partners to shape agricultural solutions to global existential challenges. She holds an adjunct faculty status at Texas A&M University, where she is a tenured professor and recognized for innovative research in soil hydrology, pedometrics, and global soil security. And so just before we launch into Cristine's talk, I want to remind you that you can put any questions you have for the speakers in the questions box, and you can go to the Padlet. The website is listed there as well during the meeting, and that's going to be open after as well. And so with that, Cristine.
All right, thanks, Dan. I take it you can see my slides, okay?
Yeah, we can see them.
Okay. Well, hello, everybody. It was great to hear John's talk, because I think all I'm going to do is reiterate what he says with maybe a different set of slides and a different set of focus. But that's good, because John and I did not sync our talks. And it tells me that we're all thinking the right way about how to get carbon measurement or understanding of carbon change as a result of management change scaled up, so that we can actually participate in carbon markets with certainty at reasonable cost. So what I think what I would like to do first today is just kind of share some of my understanding of where this space is. I think John gave like a really nice overview of like the markets and where they are and what they're requiring. And then a lot of my experience has just been like in the field trying to figure out how to make it work. And going from an academic at a Texas A&M University to the Soil Health Institute has really, the last couple of years of the Soil Health Institute has really focused my thinking on how we're going to make this work. So the big theme that I'm talking about is how we're going to get carbon measurements to scale. And it's whether, we could use measurements for modeling, and we can use measurements for improving modeling. We can use measurements for helping with uncertainty in modeling, or we can just measure. And I think John covered a lot of those concepts really well. So I'm not going to talk about that. And I am going to try to figure out how to advance my slides. Okay. So I like when I'm talking to new audience, especially I think this audience is a stronger academic audience. And I just want to introduce the Soil Health Institute. We have a mission to safeguard and enhance the vitality and productivity of soil through scientific research and advancement. And a lot of who we are at the Institute are scientists, primarily soil scientists, biogeochemists, microbiologists, and we also have modelers and economists. And so that's a little bit about Soil Health Institute. So let's talk about where we are in understanding carbon measurement to scale. And I'd like to start out with what we know, and I think John introduced this really well. We know how to measure carbon, right? We know how to do dry combustion. We know how to measure it with spectroscopy, good to go. We know how to spatially sample farms, paddocks, regions, right? There's been a lot of work in this area, and I think that one of my scientific communities for my whole career has been the pedometrics community, and this is what we talk about, like, you know, how to do the sampling job. And then we know soil organic carbon changes with management. John showed some nice slides on that. And we know, I just thought I'd throw this in, soils with coarse fragment modifiers are the hardest. Those of you that don't come from a soil science or pedology background, a coarse fragment modifier is something greater than 2 millimeters. And when we have to use a modifier, it means our soils have more than 15% by volume of these coarse fragments. And really below 15%, I would say it's not so hard. But when the soils have to have a modifier, we start getting into, oh goodness, I don't know if we can do a measurement-based estimation of carbon to scale and at cost. So anyway, that's just a little bit of what we know. But what I really want to focus on today is where we can grow. Like what needs to happen here. And anytime you're thinking about carbon, I can't tell you how many emails, phone calls I get. I want to say daily, but sometimes I don't answer my phone or look at my emails in a day, but weekly, about people that just want to know, hey, I have this, how many soil samples do I need to know how much carbon I have in my soil? And I always just take a deep breath and then choose not to answer. No, seriously, when we think about this question, we need to think about the cost, how much certainty we need in the measurement, and how credible you want to be in the delivery of that information. And I tried to think about an equation for it, and cost, you know, as certainty goes up and credibility goes up, so does cost. But there are different ways to get the cost down and certainty up, right? And ultimately, as scientists informing a market space, we want to always do this credibly. And I think John certainly talked about this too. You know, he talked about uncertainty and quantifying what we do know and what we don't know. He talked about counterfactual, and it's really about keeping the story straight and keeping it based on data and what we know, okay? This is the big one. How do we convert scientist thinking to commercial application? I mean, let's be real, carbon markets are a commercial endeavor. And this is, I think, where as scientists, when we really think about translating our knowledge, we also have to translate our art. And as a soil scientist that's been sampling soil since undergraduate, you know, there is a lot of art to soil sampling and a lot of art to thinking about soils. And traditionally, our scope and our thinking has been around the paddock, around the field, around the forest, you know, something that you can draw a fence around. And I think John started alluding to this, that we have to think more regionally if we're going to get commercial. And we also have to give up some things, like some of the conversations I hear around carbon markets, and I think, oh my gosh, we just sampled, you know, we just did 2,000 samples in a month. I'm not even thinking about those issues. We're going commercial here and we got to move. And with that, there's a very natural tension between, you know, that scientist thinking about, okay, this has to be a good measurement, and that commercial thinking is like, okay, I got to get a measurement and I'm only getting paid so much to do it. And ultimately, both of these two, this cost, certainty, credibility paradigm, along with scientist thinking versus commercial application, goes to scale, 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 scale. And we know we have some problems with scale. We know, you know, I think John called it, what did he call it? Data-driven sampling. I just call it soil science, but I say that tongue in cheek. But we know we have soil maps, but we know our soil maps are at the wrong scale if we really want to go sample carbon. And so this is one of the issues that's not talked about a lot because it's really fancy to talk about measurement, but this is just as strong of an impediment, and that's where remote sensing actually has a good space in this question. We need to think beyond the paddock. I think John's covered that in his pictures and his and looking at those numbers of samples that we need and how they flatten out as we get bigger. And then one of the things that I think that I didn't know is how amazing and good our commercial soil samplers are across the United States. There's some really good companies with amazing skill and credibility. And when I talk about that art, you know, they have the art of soil sampling at that commercial scale. So there's some positives. I just don't want to always think about like the challenges. I just think about the resources that we have, and they're pretty amazing too. Okay, so the way I thought about it was a little how John thought about it. But I want to think about measuring soil carbon stock and what are the parts, right? And so John talked about what do we measure? Carbon concentration, soil volumetric measurement, because we got to convert to stock. We can convert to stock using fixed depth or fixed mass. There's a lot of conversation about that. There's no doubt in my mind that fixed mass reduces the uncertainty in the estimate, and so that's a bonus. But at the moment, we're limited by our traditional art of sampling. But I think that's going to change very quickly. So I don't really want to get caught up on fixed depth versus fixed mass because it takes the same actual measurement in the field. Like you got to get concentration and you got to know your volume. And if you don't know that, then you can't even play with depth or mass. Where to measure? John covered that too. I think we kind of know. If you want to get a good estimate of your mean, you sample randomly. If you want to get a good estimate of your mean and reduce your uncertainty, you need a stratified random sampling. And I think we're all there in the soil science world. But once again, we're really limited. We need high resolution information on our soils. And so what I see is an ensemble between what we have with Sergo and remote sensing, put them together and use those for our stratified random sampling designs. And this is the fun part, right? How many to measure? And that gets back to that balance of cost, certainty, credibility, and this is where proximal sensing, I think, has a role to play. So just to review part one, what's the problem? We know how to sample. We take this nice sample, we know how the volume of the soil, we get the concentration, we can convert stock, but every time we take one of these samples, we have to transport it. Yuck, we have to box it up and get it to the lab, and then the lab's got to crumble this, dry it, grind it, subsample it, and then go off to the lab. So a lot of cost is lost in processing. And that's where John was talking about, like, okay, how do we reduce processing, right? And the ultimate goal, I think, is our modality, and I'm going to cover that in a second. Where do we measure? Again, John showed this too. You know, he showed us a bunch of histograms and spatial distribution, but never lose sight of this concept. John calls it a needle and haystack. I like to be a little bit more optimistic because we know where the needle is. We have remote sensing, we have spatial statistics on our side, but we still have to, even when you pinpoint the spot in the field, right? You still got to go find the needle. But John did a really nice job of explaining this, that we have this high spatial variability. The nice thing is most of the variability has a spatial structure, so it's predictable or modelable. And then any point that we choose in this field, we're looking at this carbon along this profile, and it's not consistent, and certainly management is changing it. So in this example, this is a no-till versus conventional till plot, typical plot kind of experiment, and we're looking at carbon concentrations with depth to 40 centimeters. And certainly you can imagine how a plow or lack of a plow can really change this distribution at 0 to 20 centimeters. And so we need to be able to measure at depth. And John pointed that out, that this is probably one of the biggest problem. If we could solve all those other problems with remote sensing, we're still stuck with this one, is that you can remotely sense the carbon beautifully on that surface. But if you don't know that history, management histories change and they're not recorded, then you don't really have a whole lot of ability to figure out that depth distribution. Okay, so part three, cost certainty. Uh-oh, my screen sharing has been paused. How do I unpause it? I'm gonna just stop and maybe it'll restart. Okay, there we go. Okay, so part 3, cost, certainty, credibility. There's the old adage, you get what you pay for. And the nice thing about remote sensing and proximal sensing is they have fixed costs, right? Remote sensing, fixed costs, great. Surface view only problem, what is below that surface view. Proximal sensors, fixed costs, great. We can get a deeper view, wonderful. And then we have these 2 modalities. We have ex situ proximal sensors, what John talked about, like LIBS and VisIR in the lab, and you can even do it in the field ex situ. And then ultimately, if you want to reduce your costs, if you want to get down to below $3 per sample, and I think we can get down below $3 per acre, we need to do in situ in the field and not pull cores. And I wrote the question just playing around, do you get what you pay for? And I just said, nah, we got soil science and we can leverage technology. So we can get something for a little bit here. And that's what I just kind of wanted to remind you of, like a lot of this proximal sensing. We're just looking at the spectrum, energy, electromagnetic spectrum, and we're using the spectrum to get us information. So just like you and I use our eyeballs to see visible, we can also go into the near infrared and near infrared, mid infrared lights. We can use X-ray, and people do for carbon. We can use gamma ray, people do for soil carbon. And then a lot of the remote sensing is on this side, the radio, microwave, infrared, and visible light. So just remember, it's a continuous spectrum, and we're just manipulating it to try to get information when we're proximally sensing. So what are these modalities? We have ex situ laboratory. John talked a little bit about this. The problem with ex situ laboratory is you still need to prep the sample, and there's a lot of cost. If you have to send a sample to a lab, you've just paid for boxing it, shipping it, prepping it, and that's money, a lot of money going into that soil sample. But then we can circumvent like the traditional cost of a destructive sample by using MIR, which is outstanding if you dry the soil and you very finely ground it. And there's been a new paper out. I should have put the citation, but it's out of Matthew Tingle's lab, who it's in Geoderma in 2021, volume 382. Anyway, there's this new paper. It's kind of interesting where they're adding a Z-plane detector with portable X-ray fluorescence. And essentially, we know X-ray fluorescence that carbon is too light to actually be seen with X-ray fluorescence, but they're putting this extra little sensor on that little portable PXRF and are able to see the bulk density in the carbon and get some nice relationships. Problem with it still is you still have to prep the sample, and nothing's going to be better than MIR, I don't think, at the end of the day with a prep sample. And also, this portable X-ray reflectance idea with the Z-plane sensor is really in its infancy, but I thought I would just bring it up because it is something new, and we're always interested in seeing, what's new out there. So if we use ex situ laboratory samples, we still are paying for the shipping and the prep. We still need libraries to develop calibration equations. For MIR, that's easy. We have the NRCS library. For VisIR, we have NRCS and global libraries. But this is the important need that I want to point out. We need employment of machine learning methods that give credible estimates of uncertainty. And I would always encourage anyone who goes into this space to make sure that they're employing machine learning methods that give credible estimates of uncertainty and not doing what we worry so much they do, and that's overfitting. If you overfit, you're still going to get your nice mean estimate, but you're going to be vastly under predicting how uncertain you are, which in the end of the day can get you into trouble. But we still need that bulk density measurement. Maybe we don't. John, said, there's a lot of evidence saying that it's not so important. I think it still is important because your bulk density can change with management, and that's an important shift that could get one off if you're just looking at carbon concentration. But I do agree that we don't need to be as precise with our bulk density estimate as we need to be with our carbon concentration. So I'm very much aligned with that thought process. So spectral libraries, John again also showed a nice image of this, but you have your dry ground soil. So this is a Vis-NIR example. So MIR, the sample would be way better ground than that. And you shine a light on it and you measure the reflectance. This is a nice reflectance waveband. So we have reflectance on the y-axis and wavelength on the x-axis. And then we create a model. So when we're using Vis-NIR, the big thing is can we do it in the field? And yes, of course we can. I would say 8 years ago, that was a question. Now we've figured it out. We can scan with Vis-NIR. We can scan in the field at an unknown and variable moisture content, and we can predict carbon with that. All we need is these global libraries, and then another library which we call an EPO library, or some people use a different methodology called with a linear calibration. But either way, we can do it. It is doable. And I think the best example of that should be in situ field, ex situ field, that's correct. We have to pull the soil core, and then we can measure it with MIR and gamma ray detector. So the only problem with the gamma ray gives us bulk density. It's very good. The only problem is we're creating and shooting it's X-rays, and I'm not a big fan of X-rays in the field, but it works. And so that's an example of ex situ field. Some examples of in situ field. I can see that I just covered up everything with this citation, but the nice thing and where we save the money and where we can get under $3 a sample is there's no prep to happen. We can push something into the ground. So usually it's a Vis-NIR mounted something. I wrote up here a soil penetrometer, and you can push it in as deep as you want, or you can. And also, John showed the picture of the yardstick, which is being developed under the same project as the penetrometer, where it's a handheld and it's spiraling into the ground. And so the physics for the concentration measurement is the same, but the physics for the bulk density measurement is slightly altered. And so that's I think our greatest chance of doing in situ spectroscopy for carbon. Anyway, I also wanted to show there's another in situ method called inelastic neutron scattering. This is the little instrument. It's the data is coming back pretty good on it. Again, though, we have a radioactive source in the field, and that's probably its biggest limitation. And it also is limited to 30 centimeters depth. And this paper talked about showing that the calibration did not have to be so local, but I would say that up until, that is still some of a question is how local the calibration is. And then this is that in situ Vis-NIR mounted penetrometer. So essentially we have a load cell that is measuring resistance, and then we have a window with a light source and the Vis-NIR fiber optic. And this is an old prototype that we had, and essentially we're measuring soil carbon in the field and with depth. So it's a continuous depth measurement of carbon concentration and a continuous method of bulk density, so that you can do your depth-based or mass-based estimate of carbon. And then lastly, so these are just some examples. This is in situ using a dried ground NRCS spectral library. And we can see that we can not only just predict organic carbon, but we also can get clay and organic carbon and other items. And then also we are able to take that Vis-NIR signal that gives us information on clay content and water content, and the penetration resistance from the load cell, and do pretty good estimates of bulk density. And if you're interested in some of that work, it's been recently published in Soil and Tillage. So my big picture here is just to say, that we've got to think about this whole problem in context. Whatever instrument we design, it needs to be, the data acquisition needs to be easy, the prediction modeling needs to be rugged. We're going to get that carbon stock estimate, but we also have to realize it's got to be integrated with optimized spatial sampling. And this is one of the things that I've just kind of learned from going from academia to non-academia, is that, scientists can put these things together, but when it's time to go to market, when something is ready, that it's all put together and it's as push button as it possibly can. So we really need to think about the context, the scale, the sampling design, and all of the pieces more holistically and put the pieces together. And that's essentially my summary. I think we are ready to convert our scientific know-how to measuring soil carbon at scale. All the pieces are there, but we have to keep things in context and remember that balance between scientific know-how into commercial application. All right.
Well, thank you, Christine, and thanks to everyone for putting questions in there. We'll get to as many of them as we can. So one thing that's come up is this that you've mentioned is we're sort of transitioning from researchers collecting soil carbon to it's being done for carbon markets. Is there a risk that all of this carbon data is going to be private data and there won't be kind of general knowledge coming out of it? It'll be really like, is all the future carbon data going to be private?
I mean, that's one of the things where I think not only that like private companies may be collecting this data, but they're also collecting the data on private land. So the question is, I mean, there is a privacy issue associated with this data. So I think whether it's a private company or a not-for-profit, that you still have to respect the privacy of the people whom you collected the data from. So there are a lot of issues with, like at Soil Health Institute, we're not-for-profit, so the data that we collect and when we collaborate, we ultimately get to publish our results, but we aren't going to publish, geo-reference data from people's paddocks. That's just not something that is appropriate. So I don't know if that answers the question, right? There's just all sorts of privacy issues on top of or underneath the commercial versus public good question.
And so one of the things you talked about was kind of developing these technologies. Like, do you have a sense for people who are listening of, something that's just being developed today? Like, does it take a year or 5 years or 10 years to get out where people can use it?
Well, that's a great question. I know for our Department of Energy project that we have with the penetrometer and the handheld, our estimate is about a year and a half before we de-risk the commercial scalability. We're always trying to be ambitious and get moving, right? Because the market's now and the technology is like trying to catch up to it. I think it always depends on investment, right? Like the best example is when the United States decided to go to the moon. And we invested in it and we paid for it and it happened very quickly. And right now there's more investment than I've ever seen in proximal sensing techniques. I've been working in proximal sensing my whole career. And it's never been so interesting to people with money before. So I don't know, we're just gonna have to see how it rolls out. I would say best case scenario, 2 years.
Okay. Well, thank you. One thing about this platform is they do cut us off right at 4 o'clock Eastern time. So I think there'd been some issues with the Padlet, but I think the link is working there now. So before we disappear here, you should be able to see the link for the Padlet in there, and I hope to see many of you on there. And I just want to thank both of our speakers for their presentations today. And I look forward to seeing many of you at our next seminar in August. So thank you, Christine. Thanks, John.